Good afternoon, everybody. Hope you're all healthy and safe at home. Let us continue with our section of Hilbert spaces. So, in this lecture, what we are going to discuss is we are going to discuss about the concept of basis. Now, we all might have heard about the term basis in algebra, in topology, and all other in various subjects. So, here we are going to discuss about the basis of a normed space. Okay, the concept is almost similar only. Let's see the definition. A sequence set xi where I varies from 1 to infinity is called a basis of a normed space X if for every x element of X there exists a unique series summation I greater than equal to 1, that is I varying from 1 to infinity, AIXI that converges to that point X. So in turn we can say that sequence set Xi is said to be a basis if every element of the normed space X can be written as the summation I is greater than equal to 1 AIXI. Right, that is the basic definition of a basis, right? Every element of that set can be expressed as a linear combination of that particular system. So here also a sequence is said to be a basis if every element of that normed space X we can find a unique series summation I greater than equal to 1 AIXI which converges to this point. So converging means it can be written as a sum of these elements. So next we shall move on to the theorem 2.1.10. The theorem is simple. It states that a complete orthonormal system in a Hilbert space H is a basis in H. Okay. Every complete orthonormal systems in a Hilbert space will form a basis in that space H. Now let's see how we can move to how we can prove this. So first of all we shall consider we need to show that every orthonormal system is a basis, right? So let us consider an element in the Hilbert space H. Okay, then by Bessel's inequality, what can we say? By Bessel's inequality we can have summation I equal to 1 to infinity mod inner product x ei whole square is less than or equal to whatever norm x square. So norm is a finite value, so this is finite, right? This is our Bessel's inequality. Now we are given a complete orthonormal system, right? Given set ei is a complete orthonormal system. Now since this is a complete orthonormal system, I am going to use a corollary which we had done before, that is by corollary 2.1.3. If we have a complete orthonormal system, we can find the term summation I equal to 1 to infinity inner product x ei is an element of that space. Just go through the corollary. The corollary is nothing but if we have a space X then and an orthonormal system ei, okay, this is orthonormal, then summation ei belongs to the space. So here we are having the Hilbert space H, okay, and we have an orthonormal system, and instead of ai or alpha I am using inner product x ei. Okay, so this is the corollary. If we have an orthonormal system, the elements of this form or this term is an element of the Hilbert space. So I am considering this to be y. So y is equal to summation I equal to 1 to infinity inner product x ei is an element of H. Now let us see what is the value of inner product y minus x ei. Okay, x is an element of H and y is again an element of H. Let me see. What is y? Y is nothing but summation I equal to 1 to infinity inner product x ei minus x comma ei inner product. Right? So I'm going to just split this up. So what will it be? It will be summation I equal to 1 to infinity inner product x ei comma ei minus inner product x ei. So first term ei and the next term and ei, and I am taking the minus term common by the property of inner product. So this much is clear. So from this I am again going to take this constant, that is summation I equal to 1 to infinity inner product x ei comma ei. Right? I am taking this term constant minus inner product x ei. Now ei is an orthonormal set, right? So when will whenever I is same, these two are same, we get 1, and for all other i's, that is whenever the I is different, we'll get a 0. So what will be the only term that is there? Inner product ei will be 1 and inner product ei will be 0 for every other I, right? So inner product y minus x into ei is nothing but inner product x ei minus inner product x ei, because all other terms of the summation will become 0, only this term remains. So this is 0, right? Now I am going to use lemma 2.1.6. So by the lemma it states that if we have an orthonormal system and if we have an element which is orthogonal, Fi is orthonormal system, and if x is orthogonal to Fi, then we can say that x is equal to 0. This was our lemma 2.1.6. So here we had ei, set ei was our orthonormal system, right? And just now we have seen that inner product y minus x ei is 0, that is y minus x is orthogonal to ei. So by lemma this implies we can say that y minus x is 0, or I can say that y is equal to x, or by definition of y we can say that x is nothing but summation I equal to 1 to infinity inner product x ei, that is x is the linear combination of elements of the set ei, right? So by definition, so here instead of ai I have inner product x ei. So by definition of basis we can say that set ei is a basis for our Hilbert space. So this implies the orthonormal system forms a basis. So since it was an orthonormal system only, we could use our Bessel's inequality and the lemma and all. Now for we need to show that it is unique also, right? That is the expression, the series expression is unique. So suppose that suppose x is some other term, like suppose x is equal to summation say ai into ei. Okay, now we have inner product x ei will be nothing but inner product x is summation ai ei, right? So summation ai ei comma ei. Now I am taking the summation ai common, summation ai into inner product ei. So where I varies from 1 to infinity. So here again, by the definition of orthonormal system, this is 1, this becomes 1 when I is equal to I, and all other terms will become 0. So this is nothing but ai. So ai is nothing but inner product xei itself. If x was considered to be some other summation, if the constant was changed also, we get that, we can conclude that ai is nothing but inner product xei itself. So there is only one unique way of expressing x as a linear combination of elements of the set ei. Hence, by definition, ei forms a basis of H. So I think the proof is clear, that any complete orthonormal system in H is a basis in H. Now, with the help of this theorem, we can also state a corollary 2.1.11, that is, every separable Hilbert space has an orthonormal basis, right? So if you recall, in the previous lecture we had seen that every separable Hilbert space has a complete orthonormal system, right? So if you are considering a separable Hilbert space, this space complete orthonormal system, and that complete orthonormal system will be a basis. That was the theorem, previous theorem which we had seen, that is, every orthonormal system in a Hilbert space forms a basis. So we know that every separable space has a orthonormal system contained in it, so that system will form the orthonormal basis. So with this we shall wind up today's session. Thank you. Stay home and stay safe.